Hello everybody. In the previous class, we discussed uh, with this kind of result that characteristic roots when the characteristic roots of this system, this was the system, and when the characteristic roots of this system were real and distinct, we discussed an example of on that case, that how to find the general solution of this kind of system. Now we consider the second case where the characteristic roots are complex conjugates. Okay, this is the second case where the characteristic roots are complex conjugates. And if time permits, I shall discuss this third part, that means when these characteristic roots are real and equal. Hmm. So let us directly go to this second case, the discussion of the second case, that when these characteristic roots lambda 1 and lambda 2 are complex conjugate. In that case, how can we find the solution of this given differential system, or the system of differential equation with constant coefficients? So this is the case number 2. And if these two are characteristic roots, then you see this lambda 1 and lambda 2 will be complex conjugate to each other. That means lambda 1 can be written in this fashion, that a plus I into b, and lambda 2 can be written in this fashion, that a minus I into b. Okay, so over here lambda 1 and lambda 2 are two complex conjugates. This is a plus ib and a minus I. And in such cases, you see, we considered a trial solution in this fashion, that x was considered to be is equal to some constant capital A into e to the power of lambda t, and similarly y was considered to be this kind of to have this kind of trial solution, b into e to the power of lambda t. Now particularly if we put lambda is equal to lambda 1, or a plus ib, in that case you see x will have this kind of expression, some capital A. It is written in terms of a star. Okay, fine. So capital A1 star into e to the power of a plus bi. That this is actually the value of lambda. That is actually lambda 1 multiplied by t. Similarly, y will have this kind of expression, that b1 star is equal to e to the power of lambda. Lambda means a plus b into I multiplied by t. So this is for lambda 1. Okay, so this solution comes for lambda 1. This is the solution for lambda 1. Similarly, if we put lambda is equal to lambda 2, we will get this kind of solution, the values of x and y. A, in place of a, they have written a2 star e to the power of lambda 2 into t, and similarly b2 star into e to the power of lambda 2 into t. That gives us the value of y. So in this fashion we will get two different set of solutions for x and y. But remember, over here you see these two are complex numbers, where our given system is a real differential system, and so we expect real solution of these two of this given differential system. But over here these two are represented in terms of complex numbers. but we are not expecting this kind of complex solutions. So we have to from these two solutions we have to extract the two different independent real solutions. We have to extract two set of different independent real solutions from this given information. All right. Now, how can we extract this solution? It can be shown that the real part of these solutions, the real part of these solutions and the imaginary part of these solutions become two independent solutions of the given differential equations. I am repeating this one again. It can be shown that the real part, one is real part and another is the imaginary part. The real part and the imaginary part of these two equations, of these two solutions, will produce two linearly independent solutions. And from that linearly dependent solution, if we expand these solutions over here, then after expansion we will have this kind of solution. This would be the expression of x, and this would be the expression of y. And in that case, this is the real part. This much is the real part. This real part and the complex imaginary part, this real part and imaginary part, they will together produce two linearly independent solutions of the given differential equation. And from that two, this is the real part and this is the imaginary part. And if we consider the linear combination of these two these two solutions, then we will get the final general solution of the given differential equation. So this is the basic technique or a blueprint. I am not going to show you all the detailed calculation, because calculations are you can go through these calculations first of all, and secondly calculations are not important for the this kind of theoretical calculations. At least these are not important from the exam perspective. All right. So before rather than showing this kind of detailed calculation, let me directly go to an example by which I can demonstrate this technique. The entire process is summarized in this theorem. This is the theorem under which we will be able to summarize the entire process over here, process of computing the solution. Now let's try to show you, or let's try to demonstrate the technique by which when we have two different complex conjugates, we can find the solution of a given system of differential equation. Over here, it is given that dx dt is equal to 3x plus 2y and dy dt is equal to minus 5x plus y. These are two differential equations, or the given system of differential equation. Now we consider this kind of trial solution. X is equal to a into e to the power of lambda t and y is equal to b into e to the power of lambda t. This kind of solution. Okay. Now, in this kind of solution, if we consider x is equal to a into e to the power of lambda t, in that case, what would be dx dt? dx dt. dx dt would be is equal to a into lambda into e to the power of lambda t. This is dx dt. Similarly, we can find dy dt, the derivative. dy dt is equal to b into lambda into e to the power of lambda t. So if we use all these informations, the expressions of x, y and dx dt, if we use all these informations in these two given differential equations, then what we get? Then we get this kind of expression. You see over here, in place of dx dt, we have used this expression a lambda into e to the power of lambda t. Similarly, in place of dy dt, we have used this expression that b lambda into e to the power of lambda t. Okay, so in this way we just put these expressions and we can cancel this e to the power of lambda, because this for any finite value of lambda, e to the power of lambda, this e to the power of lambda is not equal to 0. It is never equal to 0 for any finite value of lambda and t. Hmm. Therefore, we can cancel this e to the power of lambda t from both sides, and ultimately, after cancellation, we get this kind of system involving two unknown quantities, capital A and capital B. And now if we eliminate these two unknown quantities, capital A and capital B, then we will get a determinant. How to construct this determinant? These coefficients 3 minus lambda, then this 2, then this minus 5, and this 1 minus lambda. All these four coefficients will construct this determinant. Okay, and this determinant should be equal to 0 when we eliminate these two unknown quantities, capital A and capital B. Okay, so after elimination of these unknown quantities, capital A and capital B, what we get? We get this kind of determinant, and expanding this one, we will get this kind of characteristic equation, that is lambda square minus 4 lambda plus 13 is equal to 0. And when we solve this differential equation, this is a second degree differential equation. When we solve this differential equation, we get these two solutions. 2 plus 3 into I and 2 minus 3 into I. So we can consider that lambda 1, any one value. Suppose lambda 1 is equal to 2 plus 3 into I, and we can consider lambda 2 is equal to its conjugate value, 2 minus 3 into I. Alright. Now we consider this first value. Lambda is equal to this lambda 1. Lambda 1, that is actually 2 plus 3 into I. So if we put lambda is equal to 2 plus 3 into I in this system, in this algebraic system of linear equations, in that case we will have this type of relation. And you see, this is if we solve these two relations, over here we have two unknown quantities, capital A and capital B, and we have two equations involving these two unknown quantities. So theoretically we can solve them. And when after solving this kind of relation, you see over here the solution is not given, so you will have to show the solution steps. Here you have to show the solution steps, or it may appear that the example is very small example, but there are step jumps that has been that is to be shown in this example properly, at least if you write them in exam. And if you practice them, you please try to show this kind of intermediate steps. Okay, so if we solve this system, then what we get? We get this solution. A is equal to 2, and then we will get B is equal to minus 1 plus 3 into I. Okay, so these are the two values of capital A and capital B. So what was x? X was equal to, we considered that x was equal to capital A into e to the power of lambda t. So if we put capital A is equal to 2 and lambda is equal to this lambda 1, that is 2 plus 3 into I, then we will get this kind of value of x. X is equal to capital A, this is our capital A into e to the power of lambda into t. Here, so in this fashion we will get the expression of small x. Now what was y? Y was equal to capital B, capital B into e to the power of lambda into t. Now what is capital B? We got this value of capital B. Capital B, we got it that capital B is equal to -1 plus 3 into I. So if we put this expression of capital B over here, and what is lambda? Lambda is equal to 3 plus 2 plus 3i. Lambda is equal to 2 plus 3i. So over here, if you put the value of capital B, this is the value of capital B multiplied by e to the power of lambda into t. So in this way, we will be able to compute the expressions of x and y. This is the expression of x and this is the expression of y. But remember, these expressions are written in terms of complex numbers. These are solutions, fine, but these are written in terms of complex numbers. These are complex solutions. We are interested in real solution. Okay, these are complex solutions. We are interested in real solutions. Then how can we compute the real solutions? You see, we have a formula that e to the power of I into theta, that is called the Euler's formula. E to the power of I theta is equal to cos of theta plus I sine of theta. We have this kind of formula. This is a well-known formula in complex numbers. So if we apply this formula in place of theta, we can consider 2 plus 3i. So if we apply this formula in this expression of x and y, all right, then we can expand them in this fashion. You see, this expression of x can be written as e to the power of twice t. You see this expression, this x can be written in this fashion: 2 into e to the power of twice t into e to the power of 3i into t. All right. So whenever this e to the power of 3it is to be replaced by using this kind of formula. So over here, what is theta? Theta is equal to 3 multiplied by t. So 3it is there over here. So we can consider theta is equal to 3t. Therefore, this e to the power of 3it, over here you see e to the power of twice t is there, no problem is there, and this 2 is multiplied over here. Okay, so it is also fine, and this e to the power of 3it can be expanded using this kind of formula: cos theta plus I sine theta, where theta is equal to 3t. Okay, so that would be cos of 3t plus I sine of 3t. So in this way, we consider the expansion of x. Clear? And similarly, we can consider the expansion of y. What is y? This y can be written as -1 plus 3 into I. This is a complex number, fine. Then multiplied by e to the power of 2 into t, multiplied by again e to the power of 3i into t. So again, this e to the power of 3it, this expression e to the power of 3it can be expanded by this kind of formula. And after expansion of this e to the power of 3it, what we shall have? We shall write this kind of expression: cos of 3t plus I sine of 3t. Got it? So over here you see this is a complex number, cos of 3t plus this I sine of 3t, and this is another complex number, -1 plus 3i. This is another complex number. So whenever we multiply all these complex numbers, you see over here this e to the power of twice t will get common, and the remaining part will have this kind of expression. The remaining part will have this kind of expression. So from these are actually the expansion of x and y into real and imaginary part. So we can identify the real part firstly. What would be the real part of x? Real part of x over here, the real part of x is equal to e to the power of twice t multiplied by 2 into cos of 3t. That is the real part. So this is the real part of x. X is equal to 2 into e to the power of 3 into cos of 3t. That gives us the real solution of x. Similarly, what is the real part of y? Over here, e to the power of twice t, again multiplied by minus cos of t minus 3 sine of t. So this gives us, after taking this negative sign common from this term, sorry, and from this term, after taking this negative sign common, we will have minus e to the power of twice t multiplied by cos of 3t plus 3 sine of 3t. So in this way, we compute the real part of x and y. Similarly, if we compute the imaginary part of x and y, what would be the imaginary part of x and y? This e to the power of twice t multiplied by 2 into sine of 3t. This gives us the expression of x, the second expression of x from the imaginary part. Clear? Similarly, the imaginary part of y, that would be e to the power of twice t multiplied by 3 cos of 3t minus sine of 3t. So in this fashion, we will have this imaginary, this second expression of y. This is the expression of y. Here, so these two expressions are formulated from the real part of the complex solution, and these two expressions are formulated from the imaginary part of the complex solutions. Got it? And therefore we can take the um, linear combination of these two solutions. So what would be this C1 multiplied by this expression plus C2 multiplied by this expression? That would give us the expression of x. That would give us the general solution of x. All right. Similarly, C1 multiplied by this expression and C2 multiplied by this second expression, that would give us the general solution y, where C1 and C2, these two are two arbitrary constants. So in this fashion, we will be able to compute the general solution of the given differential equation, where C1 and C2 are two arbitrary constants. Okay, so that is the technique that I wanted to demonstrate when the characteristic roots of the given system are complex conjugate of each other. Here we discuss the third case, when the characteristic roots of the equations are real and equal. All right. That means when this lambda 1 and lambda 2, when this lambda 1 becomes is equal to lambda 2. In that case, we will have to find out the solution of the given differential system. And how can we find the solution? You see, whenever one solution is x is equal to, say, lambda is equal to lambda 1, lambda is equal to lambda 1 or lambda 2, when this lambda 1 and lambda 2 are equal, in that case we expect that the solution to this equation would look like this: a into t into e to the power of lambda t. Mind it, one small t is there, and a into t into e to the power of lambda t, and b into t into e to the power of lambda t. One can prove all these results. I am not going to prove this kind of t. What for did you get this kind of t, etc. You can go through these calculations. And another set of solution would look like this: a1 multiplied by t plus a2 into e to the power of lambda t, and the second one would be b1 into t plus b2 into e to the power of lambda t. These are the two possible solutions. Now we will need to find out the values of these constants a, b, similarly a1, a2 and b1, b2. So in the subsequent example, I am going to show you an example where we can find these values of a, b, a1, a2, b1, b2 and all. Hmm. And the total discussion has been summarized over here. Hmm. You see over here, this kind of solution a into t to the power of lambda t and b into t to the power of lambda t. In such places, we can also consider simply a into e to the power of lambda t into b and b into e to the power of lambda t. This is one set of solution, and another set of solution would be like this: x is equal to a1 t plus a2 into e to the power of lambda t, and y is equal to b1 t plus b2 into e to the power of lambda t. Now, how can we compute this capital A, capital B, and then this a1, a2, b1, b2? Okay, we will have to show this result by an example. And if we can find the values of capital A, capital B, capital A1, A2, capital B1, B2, then by taking the linear combination, that means first solution multiplied by C1 plus second solution multiplied by C2. Taking the linear combination, we will be able to compute the general solution of this given differential system, or system of differential equations. So let's go through an example. Let us consider this example: dx dt is equal to 4x minus y, and dy dt is equal to x plus twice y. So we first assume that x is equal to a into e to the power of lambda t. If x is equal to a into e to the power of lambda t, then we can compute dx dt. Dx dt is equal to a into lambda into e to the power of lambda t. This is dx dt. Similarly, from this relation, you can compute dy dt. Hmm. dy dt is equal to capital B into lambda into e to the power of lambda t, like this. So if we use all these expressions of x, y and their derivatives dx dt and dy dt in this relation, okay, what we get? We get this kind of equation. We get these two equations, and as because this e to the power of lambda t, this e to the power of lambda t is never equal to 0 for any value of lambda and t, we can cancel e to the power of lambda t from both sides. We can cancel all this e to the power of lambda t from both sides, and ultimately we will be able to have these two equations with two unknown quantities, capital A and capital B. Now, if we eliminate these two unknown quantities, capital A and capital B, then what we get? We get this kind of determinant. The determinant is formed by the coefficients 4 minus lambda, then it's the coefficient of minus b, that is actually is equal to minus 1. So we write minus 1 over here. Again, the coefficient of a is equal to 1, and 2 minus lambda is there. So in this fashion we form the determinant. Okay, if this determinant is equal to 0, then by expanding this determinant we will have this kind of characteristic equation, and it has two repeated roots. These are the repeated roots 3 comma 3. So over here lambda 1 is equal to 3, and that is equal to lambda 2. Now, if we put lambda is equal to 3 in this equation, in these two equations, by putting lambda is equal to 3, what we get? A minus b. If we put lambda is equal to 3 over here and 3 over here, in that case, what we will have? we will have over here a minus b is equal to 0, and if we put lambda is equal to 3 over here, again we will have a minus, sorry, a minus b is equal to 0. So we actually get same equations. In both of these two cases we are getting same equation. So what we shall have, we shall finally have the relation that a is equal to b. So we shall have this kind of relation, a is equal to b. So whatever be the value of a and b, they must preserve this relation that a is equal to b. This relation has to be preserved. Therefore, we can arbitrarily choose a is equal to b is equal to 1 or 2 or 3 or whatever you like. Over here, they have taken the value a, the common value of a and b to be equal to 1. So if capital A is equal to 1 and b is equal to 1, what was x? X was assumed to be is equal to capital A into e to the power of lambda t. Now capital A is equal to 1. Therefore 1 into e to the power of lambda. What is lambda? Lambda is equal to 3 into t. So we have, that is actually is equal to 3 into t. So we have this expression of x. So x becomes is equal to e to the power of 3 into t. Similarly, what was y? Y was equal to b into e to the power of lambda t. Now what is b? B is equal to 1 and lambda is equal to 3. So we shall have e to the power of 3 into t, and that becomes is equal to simply e to the power of 3 into t. Here, so over here we have this expression of y. So in this way we get the first set of solution. X is equal to e to the power of 3t and y is equal to e to the power of 3t. We get the first set of solution. Now we need to compute the second set of solution. How do they look? They would look like this, that a1 t plus a2 multiplied by e to the power of lambda t, or lambda is taken over here is equal to 3. So we have writing e to the power of 3t, and what would be y? Y would be is equal to b1 t plus b2 into e to the power of 3t. So if we now put these two expressions of x and y in this equation, in this equation number 95, what is this? Equation number 95 is actually the given equation. So we have taken x is equal to, a1 t in plus a2 into e to the power of 3t. Then what is dx dt? You see, dx dt is equal to a1 a1 sorry a1 into e to the power of 3t by chain rule. This is the, you can consider this a1t plus a2t as the first function and e to the power of 3t as the second function. Okay, so derivative of first function means a1 into e to the power of 3t, the second function, plus the first function remains fixed, a1 t plus a2. Derivative of second function means derivative of e to the power of 3t, that remains b is a e to the power of 3t multiplied by 3. So in this way we compute dx dt. Similarly we can compute dy dt. We can compute dy dt, and we put this, all these expressions of x, y, dx dt and dy dt, all these expressions in the given differential equation. What is the given differential equation? This is the given differential equation. This is the given differential equation. So we put the expressions in this given differential equation. Okay. So if we put these expressions after simplification, all right, After simplification, we will get this kind of relation. After simplification means whenever we cancel out this e to the power of 3t from both sides, this e to the power of 3t, and after cancelling all this e to the power of 3t and making them simple, we will get this type of relation. And that is to be true for all value of the parameter or the variable t. It should be true for all value of the variable t. And therefore it must be an identity. All right, it must be an identity. And what is the meaning of identity? That the similar coefficients on left side and right side both should be true. On the right side, what we have on the right side, we have 0. So we can write 0 multiplied by t plus 0. Over here again, we shall write 0 multiplied by t plus 0. So if we compare the similar term, that means the constant term is to be compared with this constant term, and this coefficient of t is to be compared with this coefficient, that is actually 0, the coefficient of the variable t. Therefore we can say that this a1 minus b1, that should be is equal to 0. This a1 minus b1 should be is equal to 0. Similarly, a2 minus a1 minus b2, that should also be equal to 0. So we have these four relations. Although it looks four relations, basically these are two relations. You see, this relation and this relation, these two relations are same. Similarly, this relation and this relation, these two relations are same. So we basically have two relations. This is one relation. From this relation, we can have this result that A1 is equal to B1. From this relation, we can have the result that E1 is equal to B1. Okay, and from this relation, we can have the second this kind of result that B2, or we can write A2 minus B2 is equal to our A1. So you see, we have four unknown quantities, A1, B1, A2, B2. But we have two relations. This is one relation and this is another relation. So this is the second relation. So we have two relations but four unknown quantities. So we cannot exactly determine what are the values of A1, B1, A2 and B2. We can arbitrarily take their values A1, B1, A2 and B2. Just we need to maintain this relation. So if we just put A1 and B1 is equal to 1, because no other extra restriction is there. So we can arbitrarily put A1 is equal to 1 and B1 is equal to 1. You can also choose A1 is equal to 2, B1 is equal to 2, it doesn't matter. So for simplicity, we are taking A1 is equal to 1 and B1 is equal to 1. So if you put A1 is equal to 1 and B1 is equal to 1, then what we have, this expression should also be is equal to 1. Or in other words, we can say that A2 would be is equal to this B2 plus 1. Got it? So again, the question of choice of A2 and B2 comes in our mind. How to choose the value of A2 and B2? So if we choose B2 is equal to 0, then what would be A2? A2 would be is equal to 1. If you choose B2 is equal to 1, then A2 would be is equal to 2. So it doesn't matter. We shall try to choose the values of A2 and B2 so that the expressions become as much simple as possible. So over here, you see, they have chosen A1 is equal to B1 is equal to 1, and B2 is equal to 0 and A2 is equal to 1, as I discussed in this case. B2 is equal to 0 and A2 is equal to 1. The most simple case. So what was x? X was equal to capital A1 into t plus a2 into e to the power of 3t. That was our choice. So if we put a1 is equal to 1 and a2 is equal to, over here this is also a2 is equal to 1. So what we shall have, this expression would be simply is equal to t plus 1 into e to the power of 3t. Got it? So in this way we will get the second expression of x. Similarly, if we consider the values b1 and b2, what was y? Y was equal to b1 into t plus b2 multiplied by e to the power of 3t. So if we put b1 is equal to 1 and b2 is equal to 0, what we shall have? We shall simply have t into e to the power of 3t. So in this way we will get the expression of y, the second expression of y. Clear? So what were the first expression of x and y? Let me write it over here. Let me clear the screen first. What was the first expressions of x and y? Both were equal to e to the power of 3t. All right, so let me write them over here. The first expression was x is equal to e to the power of 3t. That was the first expression, and y is equal to e to the power of 3t. That was the second expression. So we have two set of solutions. This is one set of solution and this is the second set of solution of x and y. So how to find the general solution? Multiply by the first solution by c1 and the second solution by c2 and add them. So what we shall have, the general solution would be is equal to c1 into e to the power of 3t. Over here you see c1 into e to the power of 3t plus c2, this c2 into t plus 1, this t plus 1 into e to the power of 3t. So c2 into t plus 1 e to the power of 3t, that is the second term of x. So in this way we get the general solution of x. Now similarly we can compute the general solution of y. So this should be multiplied by c1 plus this expression t into e to the power of 3t should be multiplied by c2. So in this way we will get the general solution c1 into e to the power of 3t, that comes from this first solution plus c2 into t into e to the power of 3t, that comes from this second solution. So in this way we compute the general solution of this given systems, where c1 and c2, these two are arbitrary constants. Okay, don't forget to write this, these two, what are c1 and c2. c1 and c2 are two arbitrary constants. All right, so in this way we are able to compute the solution of the given differential system. And this is the total discussion regarding the solution of the system of differential equation whenever the roots are repeated. The characteristic roots of the given system are repeated and real. So that's all for this lecture. Thank you for being with us.